Good morning. Can you guys hear me? One of you might unmute himself and then call in. Can you hear me? Can you guys hear me? If you're online, one of you unmute yourself and then call in. Can you see my screen? Can you hear me? Can you guys see? Can you hear me?
Professor Banerjee, we can't see your screen.
You can?
Can't.
Okay, and again.
I think there's some feedback with your.
Yeah, so yeah, it's checking in on my desktop also, so I'll turn that off. So you guys can hear and see the screen, right?
We can't see the screen.
You cannot?
No. If you're posting slides right now, we can't see it.
Can you see it now?
Yes.
Okay, good. Okay, good morning. So last time we were talking about the current voltage characteristics of a PN junction in forward and reverse bias. Since that's such an important topic, I want to quickly review what I discussed last time. So over here, we're looking at the PN junction in equilibrium, middle row in forward bias, and the third column in reverse bias. And as I said, if you look at the equilibrium condition, as soon as you join the P and the N regions, the electrons from the n side flow over and recombine with the holes, and in the process, they expose positively charged donors on the n side and negatively charged acceptors on the p side. There's field lines from the positive donors to the negative acceptors. And in the depletion region, which is shown in the lightly shaded region. And if you integrate that field, you'll get electrostatic potential shown in the middle row over here. And the corresponding band diagram is a mirror image of that, because electron energies are minus Q times the hang on just a second. A couple of students couldn't get in. Some people are having trouble. Just give me a second. I hope that's okay. I'm hoping that's everybody. Yeah. Sorry about that. Can you guys hear me and see the screen?
Yes.
Yes.
Okay, good. For some reason, some people weren't able to get in, so I had to admit them individually. Anyway, so what I wanted to do was to quickly go over the forward bias and reverse bias characteristics of a PN junction, because that's such an important topic. And as I said, if you look at this slide where I'm looking at the PN junction in equilibrium on the left-hand column, we said that as soon as you join the P and the N regions together, the majority carrier electrons from the N side spill over, diffuse over to the P side, and the holes diffuse to the right. And in the process, they recombine with each other and thereby expose positively charged donors in the N side and negatively charged acceptors on the P side and create a depletion region. Now, the positive charges have field lines pointing towards the negative charges as shown over here. The integral of the electric field gives you the electrostatic potential variation. And then the band diagram shown down below is the electron energy, which is minus Q times the voltage. Therefore, it's the mirror image of that. And once you do that, you set up an equilibrium band diagram with a built-in barrier of QV0, which then establishes what we call dynamic equilibrium. Now, what is that? That is due to the fact that even once equilibrium has been set up, you still have flow of electrons and holes back and forth, but exactly equal and opposite to each other, so that there's no net current. Okay, now what are those components due to? Well, for example, you have a few minority carrier electrons in the conduction band on the P side. Now, these don't see an electric field over here, but they do execute random Brownian motion. But once in a while, they'll accidentally appear at the edge of the depletion region, where they do see electric field and they get swept right across. Okay. Now, that current is opposed by the diffusion of electrons from the N side. Remember, that's the majority carrier this way. Okay. But once the barrier has been set up, the diffusion rate is much slower than right at the onset, because now I can only diffuse the very few electrons which are up here in energy above this barrier, QV0, right? Remember, the electron distribution as a function of energy is given by the density of states times the Fermi-Dirac distribution function. And basically what happens is you'll have very few carriers right at the band edge because the density of states is 0. Then it'll go up, but then it'll die down more or less exponentially because the Fermi function dies down exponentially in the Maxwell-Boltzmann limit. Okay? And it's only the high energy carriers with energy greater than QV0 which can diffuse across. Okay, so that's what establishes the dynamic equilibrium. Now, one thing that I've emphasized again and again is this opposing drift current. Normally, although drift currents are proportional to electric field, in this special case, the drift current is independent of the electric field because it's a supply limited current. All right. Now, one other thing that I wanted to point out is, in this case, in this PN junction, although I have electrostatic potential variation, if you hooked up a voltmeter to the two sides, you would not be able to measure that voltage V0, okay? Because it turns out what you measure with the voltmeter is not just the electrostatic potential difference, but it's a sum of the electrostatic potential plus the so-called chemical potential, where the chemical potential is governed by concentration of the species. And the two together give you what's called the electrochemical potential, which is also known as the Fermi level. And since in equilibrium, the Fermi level is constant everywhere, there is no voltage that you can measure with an external voltmeter. Now look at the middle column. So if you now apply a forward bias, VF, the positive terminal is hooked up to the P side, negative terminal to the N side. Therefore, the electron energies on the N side go up by QVF, because electron charges are negative. Now, the opposing drift current doesn't change, it's supply limited, but the forward current in this direction now goes up exponentially with voltage, because now since the barrier is lower, it's VF, V0 minus VF, clearly you have more carriers available at these lower energies, and therefore these diffusion current components go up exponentially with voltage, while the opposing drift currents are independent of the voltage. Similarly, in reverse bias, down the barrier goes up. There's even fewer carriers overhead these very high energies. Therefore, the diffusion currents basically go down to zero. The opposing drift currents stay put. Okay. Next, we went to the analysis of the calculation of the IV characteristics in forward bias. So let's go through that again, because it's very important and it's kind of tricky. There's a lot of subtle things in the analysis. Okay, so let's review this slide again, where we went through what's known as a Shockley ideal diode analysis. Okay, so what does that mean? Well, in the ideal diode analysis, we assume that there's no generation recombination of carriers within the depletion region. So any carrier that is injected across the depletion region will go across and appear on this side. Similarly, any electron that's injected will go across without any generation recombination. Therefore, that current is going to be constant. And then, of course, when the electron goes into the p side, it will recombine with the holes, and that's what establishes this concentration gradient, and that establishes the diffusion current. Okay. Now, the other things that we have done in this analysis are assume we have so-called low-level injection that I explained in a second, and that have a long p-n junction region, as a result of which you only have the decaying exponential terms. You can ignore the growing exponential terms because that would have blown up. All right, so what did Mr. Shockley assume in this analysis? He said that, okay, if you look at Kirchhoff's current law, obviously the current has to be the same across any cross section, right? So if I could calculate the current at any cross section, that will be the current anywhere throughout the device. That's point number one. Okay. Now the components of the current would depend on where I'm looking. Okay, but the added components always have to add up to a constant value of I. Now, what are the four possible components? We've said that in general you can have hole diffusion current plus hole drift plus electron diffusion plus electron drift, right? So those are the four components. Now, not all four are going to be important all the time, all right? Now, let's start off by looking very far away from the junction, where the minority carrier concentration has died down exponentially to a constant value, and therefore the majority carrier concentrations are also constant. If the carrier concentrations are constant, what will happen to the diffusion currents? Obviously, they have to be zero, because diffusion currents are governed by dN dx or dP dx. Therefore, if the concentrations are constant, the diffusion currents have to be zero. So it only has to be drift. Now, which drift component? Holes or electrons? Well, the drift currents are proportional to the electric field times the carrier concentration, right? Therefore, on the P side over here, it has to be mostly hole drift, right? And there'll be some electron drift also, but that's going to be orders of magnitude smaller because the minority carrier hole concentration is orders of magnitude smaller. Similarly, on the N side, it's mostly far away from the junction where the carrier concentration profiles are constant. It has to be mostly electron drift. You can ignore the hole drift current, all right? Now, let's go back to the vicinity of the depletion region and see how we can calculate the total current. So the claim is I can add the minority carrier hole diffusion current at this edge of the depletion region to the minority carrier electron diffusion current at this edge of the depletion region, and that'll be the total current everywhere. Now, that's a tricky part of the analysis, right? Let's go through that again. So let's look at this point at the minority carrier hole diffusion current that I've calculated in the previous slides, and I'll go over that in a second again. Since there's no generation recombination within the depletion region, and because I can ignore the minority carrier hole drift current at this point in comparison with the majority carrier electron drift current, I can say that this minority carrier hole diffusion current is pretty much the total hole current, hole drift plus diffusion, because the hole drift current is negligible compared to the electron drift current. You guys with me? So I have four components in general, but of the four, I can ignore the minority carrier hole drift current at this point. Therefore, the hole diffusion current is the same as the total hole current. That's point number one. If that's the total hole current, that's also corresponding to the, if that's the total hole current, that must be the whole current going throughout the depletion region, because there's no generation recombination going on over here. Okay? Now let's turn to this edge. Over here, conversely, it's mostly electron diffusion current. And like I said, once again, that's approximately the total electron current, okay? I've now gone across and I've figured out what's the total hole current. So I can add this hole current, which is calculated at this edge of the depletion region, to the electron current at this edge, and that's going to be my total current everywhere, okay? So it's a lot of different things put together. So the only thing that we really need to do is to calculate what the diffusion currents are at the edges of the depletion region, right? And that's what we had done over here. All right. So the way you do that is by looking at the low level injection condition. You figure out that the minority carrier concentrations go up exponentially with voltage, while the change of the majority carrier concentration is ignored. And the way we did that was, you look at the ratio of the majority to the minority carrier concentration, which is given by this expression over here, in equilibrium. And then we said that in non-equilibrium, the same kind of relationship appears, but you have this applied voltage over here, okay? Now, the ratio is obviously decreasing, and because the majority carrier concentration, which is the numerator, does not change much, obviously the minority carrier concentration is the one which must increase exponentially as e to the power qv over kt. And that's only true under so-called low-level injection conditions. Low-level meaning that the change of the majority carrier concentration on a fractional basis is negligible. The absolute change, delta n, is always equal to delta p, where you have space charge neutrality, but you can ignore the fractional change of the majority carriers. And that's kind of shown in this change of these quasi-Fermi levels in these dotted lines, okay? What are the quasi-Fermi levels? Well, that's how the Fermi level in equilibrium changes under bias. So we have said that under bias, the Fermi levels are replaced by separate quasi-Fermi levels for electrons, which is EFN, and for holes, which is EFP. And you can see on the right-hand side, the quasi-Fermi level for electrons, EFN, pretty much stays the same as the original Fermi level because the fractional change of the electrons is small. Similarly, on the left-hand side, the quasi-Fermi level for holes, EFP, is kind of the same as the Fermi level, okay? And then finally, the separation between them is whatever the applied voltage QVF is, okay? And that's what you can measure if you hook up a voltmeter to the two terminals of the PN junction. You don't measure the electrostatic potential alone. You measure the electrostatic plus the chemical potential, the electrochemical potential, which is the same as the Fermi level. All right?
So could I ask a question real quick?
Yes.
When we say that it's low level injection, what does that change in terms of the math? Like which term is it that gets ignored in a sense?
Yes, very good question. So look at these ratios of majority carrier concentration over the minority carrier concentration. That's a so-called law of the junction that we derived before spring break. And that's given by e to the power QV over KT, where the V is whatever it is, the built-in junction potential V naught, or V naught minus V in forward bias, or V naught plus reverse bias, okay? So in forward bias, where it's e to the power q V naught minus V, clearly the ratio of majority carrier concentration over minority carrier concentration is decreasing, right? So then the question is it decreasing because the numerator was decreasing or the denominator was increasing? And the claim is, in low-level injection condition, you can say that the numerator, the majority carrier concentration, stays more or less the same. The fractional change of the majority carriers is negligible. And therefore, it must be the denominator which must increase exponentially as e to the power QV over KT. You with me?
Yes.
Yeah. Now, in a few minutes, towards the end of this class, we'll get rid of this assumption and we'll look at high-level injection, where the change of the majority carrier concentration is also non-negligible. And we'll see how the IV characteristics get modified. And we'll do that hopefully at the end of this class today. Okay. The other thing that we did in this analysis was assume that the P and the N regions were very, very long. Now, what does long mean? Long compared to the diffusion length. Now, if it's long compared to the diffusion length, if you look at this expression for the carrier concentration, minority carrier concentration profile as a function of voltage and position, notice that you have e to the power minus x over LP, which is the minority carrier diffusion length of holes on the N side. But remember, when you solve the continuity equation in steady state, you also had a growing exponential term, e to the power plus x over LP. Now, if it's a long device, that e to the power plus x over LP term would have blown up to infinity. And therefore, you can ignore the prefactor for that term. You retain only the decaying exponential term. And that's what I've done. So we are assuming we have long P and N regions. Now, that's also an assumption that we'll get rid of towards the end of this lecture, and in which case we'll have to retain both this decaying exponential term and a growing exponential term, and you'll get hyperbolic functions. So the math becomes a little bit more complicated. Okay? Any other questions? All right, so low-level injection and long diodes, this is what you have for the minority carrier concentration profile. And I write it down as the starting value, Pn naught, which is Ni squared over Nd, the donor concentration, plus the second term, which is written as the excess, okay? So I'm writing the total concentration as a starting value plus the excess. And since I've separated out the starting value, I have this -1 over here, okay? Now notice that this, if we added the Pn naught to this -1, that would cancel out, and I'd simply have this exponential term over here. But I choose to write that as the starting constant value shown by this dotted line, plus this excess, which is the second term in the expression over here. By the way, since I'm messing up these slides, I've uploaded a clean version on Canvas. So for study, you can always look up the clean unmarked version. Now, why do I want to do it this way? I want to do it this way because as far as diffusion currents are concerned, those are proportional to dP dx, right? Therefore, the constant term won't contribute to that. I only look at the variation in the second term over here, okay? And there's two exponentials. First, there's this exponential dependence on voltage, e to the power qv over kt, and then an exponential dependence on position, e to the power minus x over lp. And of course, the same kind of thing happens on the other side. All right? Any questions? I'm going over this again because it's kind of very complicated the first time I see it, and it's very important. And I will test you on this in the exam. So you need to study this part very, very carefully. I'll tell you which parts are not as important, okay? All right, so in the second slide over here, I'm now just showing the excess. So I'm ignoring the Pn naught and the Np naught, the dotted line. That's why this now goes down to all the way down to 0, okay? And you have this exponential dependence on position. And then we know how to calculate the diffusion currents, is dP dx. And as I said, I like exponentials because if you take the derivative, you get an exponential times 1 over LP. Or if you integrate, you also get an exponential, but now you have LP in the numerator. So in this first way of calculating the things, I'm calculating the diffusion current by taking the slope of the concentration profile. That's why I have LP in the denominator over here, okay? But the shape of the current will match the shape of the concentration profile. So the excess carrier concentration dies down exponentially, and so will the carrier concentration.
Hello, Professor.
Yeah.
I have a question.
Yes.
We only included the diffusion currents near the junction due to the minority carriers.
Right.
Near the junction, why are we ignoring the drift currents due to the majority carriers?
We are not ignoring the majority carrier drift current. We only ignored the minority carrier drift current.
Okay.
Okay. So that's why I said some of my screen got locked. I don't know why. can swipe my screen. Okay. All right, so I did not ignore the majority. I'm only ignoring the minority carrier drift current because that's always going to be much smaller than the majority carrier drift current. Okay. So therefore, as far as the whole current on the N side is concerned, I'm only retaining the whole diffusion current. Okay. And I'm ignoring the whole drift current. So the whole diffusion current on the N side is approximately the total whole current. And since there's no generation recombination within the depletion region, I can go over all the way to the P side, and there it's also the total whole current over here. All right. But the same argument, this is my total electron current, and that's why I could add the whole diffusion current at the edge of the depletion region on the N side to the electron diffusion current at the edge of the depletion region on the P side. It's very tricky. It's kind of subtle. So you have to kind of think over this just to make sure that you're counting all the four components effectively in KCL. Okay. Any other questions? All right. Now we also did the calculation by a second technique, which is the so-called charge control approach, where we integrate the carrier concentration profile and you get the total stored charge of excess holes QP or QN. And if they recombine at a rate tau P or tau N, they're being lost at a rate of QP over tau P. And therefore, clearly you have to resupply the carriers at the same rate. And that's how I can calculate the current also. And you get another way of determining the current. Now, the expressions might look different, but they're exactly the same, because if you compare this form with the form in technique A, which is shown over here, you'll see that all the terms are identical, except that in the charge control approach, you have LP over tau P, while in the diffusion current approach, you have DP over LP. And then we know that LP times LP, which is LP squared, is the same as DP times tau P, right? So the two expressions might look different, but they're exactly the same, and they should be, because I'm calculating the current in two different ways, okay? So that then gives you the final grand result, which is the current in a PN junction is this prefactor times e to the power QV over KT minus 1. And that's what's shown in this curve over here. In forward bias, it goes up exponentially with voltage, while in reverse bias, where V is negative, the first term basically goes down to 0, and I get a constant voltage independent reverse leakage current given by this expression over here. All right. Now, a couple of things that I also want to mention is if you look at the forward bias current, you'll notice a curious thing. Okay. What is that? Well, this component, for example, of the current is the contribution to the current due to the holes, right? Because that's delta PN over LP. Now, what is delta PN equal to? Delta PN equals NI square. Delta PN is over here, right? So that's given by NI square over ND times e to the power QV over KT minus 1, right? Delta PN over here is delta PN is PN naught, which is NI square over ND times e to the power QV over KT minus 1. All right. So the curious thing is the whole contribution to the current is inversely proportional to the majority carrier donor concentration on the N side. Let me repeat that again. The whole diffusion current on the N side is found to be inversely proportional to the majority carrier donor concentration on the N side. Therefore, if I asked you to double the whole current contribution in the PN junction, you have the total current, right? And I tell you that, okay, now design for me another PN junction diode where I want you to double the whole current contribution to the current. What should your answer be? Anybody who knows the answer might unmute herself and then answer me.
It would half the other current.
Very good. Excellent. So if I want to double the whole current, The answer is not doubling the p-type doping, but having the n-type doping, right? Because it's this majority carrier concentration which appears in the denominator over here, all right? Doubling the p-type doping would have halved the n sub p, and it would have halved the n-type, the electron contribution to the current. So it's kind of backwards, you see that? Now this will become very, very important in a few weeks when we start looking at bipolar junction transistors, which are after all, two PN junctions connected back to back. And that will impact what's known as your emitter injection efficiency. So I want to keep this nugget at the back of your mind, okay? So once again, if I wanted to double one component of the current, say the whole current component, I don't double the p-type doping, I have the n-type doping on the other side. It's backwards, okay? Now let's see if there's anything else. All right. So that's the forward bias, and hopefully it's a little bit clearer now. Once again, it's kind of complicated, and you really have to think through this a couple of times, review this very carefully, because I will give you some problems on this in the final exam, okay? Some of the things that I'll breeze through, I'll probably not test you on, but PN junctions, forward and reverse bias are fundamental, okay? Now, once you understand the PN junction in forward bias, reverse bias is relatively easier. So now the barrier gets increased, therefore the diffusion currents basically go to zero, but the opposing drift currents are independent of the voltage, because once again, it's supply limited. So now essentially what happens is the few minority carrier electrons that you have, random Brownian motion, no fields, appear at the edge of the depletion region, and boom, they ski down this energy slope. And because of that, the carrier concentration of the minority carrier electrons, which is already low to begin with, it's Ni squared over Na, basically goes down to zero at the depletion edge, okay? And because of that, you end up having a small diffusion concentration profile, and anytime you have a concentration gradient, you'll have a diffusion current, okay? So in reverse bias, you have a supply of carriers to the edge of the depletion region via diffusion, followed by drift, the supply limited drift current, and same on this side, okay? And these currents are independent of voltage, because as you increase the reverse bias, all that happens is the depletion region expands more and more, and the point where the carrier concentration profiles are pulled down to zero gets moved out either way, but the rate at which they go down stay the same. Therefore, the supply of carriers via diffusion, I'm not talking about the minority carriers, basically stays the same, and that's why it's the supply limited current that is independent of the field in this drift region, okay? So that gives rise to this voltage independent reverse leakage current as shown over here. Now, once again, if you look at these terms, let's see what are the important parameters, okay? So you see that if I wanted a low leakage junction, and of course, that's what you want in a typical device, what you want to do is have a long diffusion length, Ln and Lp, or equivalently long minority carrier lifetimes, tau n and tau p. The way you achieve long minority carrier lifetimes or long diffusion lengths is have a device with very, very few defects, okay? Because remember earlier on, we said that if you have a lot of defects in the device, you'll introduce energy levels in the middle of the gap somewhere, and that will help facilitate generation recombination processes, and therefore your tau n and tau p would reduce, okay? And that would then cause the leakage current to go up, all right? The other thing to point out is if you look at the Pn naught, what is Pn naught? That's given by Ni squared over Nd on the N side, okay? Therefore, to reduce the leakage currents, you actually want to increase the doping on the P and the N side, because that would reduce your Pn naught and Np naught. And that's also a little bit counterintuitive at times. If you have low doping, the leakage currents actually go up, all right? And that's what's shown over here. So now I'm looking at the reverse characteristics. That's its voltage independent current given by this term over here. And to reduce that leakage current, you have to increase these lifetimes, or equivalently these diffusion lengths, or increase the doping levels so that Pn naught and Np naught will be reduced, all right? However, as you increase the doping, although this leakage current might reduce, what can happen, however, is at high voltages, you may remember that a PN junction diode breaks down, that breakdown voltage would be reduced. So higher doping on the P and the N sides reduces leakage current prior to breakdown, but the breakdown can happen more easily at a lower voltage, all right? Okay, so forward bias, it goes up exponentially with voltage. This is known as your so-called cut-in voltage, and in most devices, that's about 0.6, 0.7 volts. We saw that depends logarithmically on the doping on the P and the N side. Is given by log of Na over Ni plus log of Nd over Ni times Kt over Q. And because that's a log function, this so-called junction potential V0, which is also known as the cut-in voltage, is a weak function of the doping. Okay. Now, as just pointed out, that this reverse leakage current is voltage independent only until the device breaks down, and that's the so-called breakdown voltage. Now, normally that breakdown voltage is not a catastrophic breakdown, meaning that if I let that device have high currents in breakdown, and then if I backtrack on the voltage, we'll retrace this IV characteristics. Okay, so it's not a catastrophic breakdown, unlike breakdown of a MOS capacitor, for example. It's a reversible breakdown, unless you get carried over and you really crank up the voltage on a diode to, maybe 1,000 volts, in which case, of course, you'd burn up the device, there'd be smoke and the metal would melt. That, of course, would be a catastrophic breakdown. Okay, you don't want to do that, obviously. Next, what I want to do is to tell you about the two mechanisms by which a diode breaks down. Okay. So now I'm looking at this high field region over here, right? So now I'm looking at this region, trying to figure out what are the physical mechanisms for the breakdown. The first mechanism is shown over here. It's known as tunneling or Zener breakdown. Okay, now you can look at it either in terms of the band diagram or in terms of the chemical bonds. Let's look at the chemical bond picture first. It's a little bit easier. So in the bond picture, remember we have all these silicon atoms surrounded by 4 nearest neighbor silicon atoms with 2 covalent bonds each, and every silicon atom is now happy because they have a stable octet of electrons, all right? But now, in this high reverse bias, I basically have a very high electric field, say, in this direction, and as a result, these electrons in these covalent bonds, which are bound electrons, would have a force in the opposite direction, minus Q times electric field. And if the force is high enough, you might pull out some of these electrons from these covalent bonds and they move opposite to the electric field. And in the process, it creates a free electron in the conduction band, okay? And of course, if an electron is ripped out of one of these bands, what is that? That is a hole, and that would then move in the direction of the electric field. And this process of covalent bond breaking can happen very, very easily if the fields are high enough, okay? That's in terms of the bond picture. Now, there's an analogous picture in terms of energy bands, which is shown above. And basically, in this picture, what I have is as the reverse bias increases, the bands get skewed as shown over here. You take the N side and you reduce those energy levels to a lower value, because remember, these band diagrams are electron energies, which is minus Q times V. Okay, so if I apply a higher and higher positive voltage to the N side, which is what I'm doing in reverse bias, these energies are pulled down, all right? Now, if they're pulled down enough, notice what happens in this part of the band diagram, okay? So what can happen is electrons in the valence band on the P side, remember the valence band is chock full of electrons. Suppose I look at electrons somewhere over here. What is the kinetic energy? Is it 0 or non-zero? Well, remember at the band edges, I only have potential energy. But as I move up in the bands, I add kinetic energy of the electrons, or similarly, kinetic energy in this way, right? So these electrons have some kinetic energy. And as they approach this depletion region, at this point, once it hits this band edge, the kinetic energy goes to 0. I only have potential energy. Remember, those are those so-called classical turning points. The reason they're called classical turning points in quantum mechanics is the analogy would be, imagine throwing a ball up a hill with a certain kinetic energy. As it goes, the ball goes up the hill, the ball gradually slows down, and then when it transforms all the kinetic energy to potential gravitational potential energy, it'll turn back. Okay, so that's the same kind of analogy over here. Now, if the electron was a classical particle, at this point it would have bounced back. Okay, but remember the electrons have a wave character. So once it hits this potential energy barrier, it's like a translucent barrier, with a finite reflection probability, but also finite transmission probability. That's this weird phenomenon of tunneling that we mentioned in chapter 2, right? So there has a finite probability of tunneling across. But if it tunnels across, what have I done? I've created an electron in the conduction band, and I've left behind a hole in the valence band. That's exactly the process that I mentioned by ripping these covalent bonds apart and creating electron hole pair by a very high electric field. As the electric field goes up, these bands become steeper and steeper. The electric field is the gradient of this band edge. And therefore, you'll notice that the barrier D, which is this tunneling barrier width, is going to get smaller and smaller, right? And remember, for tunneling, the thinner the barrier or smaller the barrier height is corresponding to the band gap. The thinner the barrier or smaller the barrier, the easier will be the tunneling. So who can tell me if you'd have more or less tunneling in germanium with a band gap of 0.7 versus silicon PN junction with a band gap of 1.1? Which would break down earlier, a germanium diode or a silicon diode?
Germanium.
Very good, because it's got a lower band gap, okay? Similarly, if the doping goes up, what happens to the depletion rate? It becomes smaller, right? Therefore, tunneling breakdown will happen earlier, all right? So that's the first mechanism. This is known as the tunneling breakdown mechanism, or the Zener mechanism, after the physicist Clarence Zener, who analyzed this first. There's a second mechanism, which is known as avalanche or impact ionization mechanism, all right? Here, it's not tunneling, it's something totally different, and you don't need a high doping level and a narrow depletion width. In fact, you want a wide depletion region. So the physics that goes on over here is as follows. Once again, I'm in reverse bias. I have electrons, minority carrier electrons on the P side in the conduction band. These execute random Brownian motion. Here they see no field because the band edges are flat. Once in a blue moon, they appear at the edge of the depletion region. That's a diffusion supply, and they get swept right across. That's a supply limited current, right? Now, suppose I look at this electron over here. What is its kinetic energy? Well, at the band edge, the kinetic energy, of course, is 0. It's seeing electric field. There's a variation of the potential energy. Therefore, the electron accelerates in this electric field. And suppose it's moved to this point. Is the kinetic energy 0 or non-zero? It's non-zero because it's away from the band edge, right? Such high energy electrons are sometimes called hot electrons. Similarly, you'll have hot holes. Now, if this hot electron gains enough kinetic energy from this voltage, energy greater than the band gap, what can happen is it can bump into one of these covalent bonds in the crystal and break one of those covalent bonds. Or in terms of the energy band diagram, it can excite electron from the valence to the conduction band. How many carriers do I end up with? Well, once this so-called impact ionization process happens, impact ionization because this energetic hot electron is impacting one of these covalent bonds and breaking it. This original primary electron will obviously have to lose some of its energy, but in the process, it creates a secondary electron hole pair. This primary cooler electron and this electron that's been excited carry on this way. The hole moves opposite to that, and they all add to the leakage current, all right? In fact, this process can be a chain reaction, and that's what's shown over here, okay? Although that's not shown clearly over here, it's shown clearly in this cartoon view, right? So what can happen is you can create a secondary electron hole pair. These keep gaining energy, and if they can gain enough energy, they can create a third generation electron hole pair, and it kind of snowballs like in a nuclear chain reaction, and before you know it, you get a very large number of electrons and holes that are created with slight increases of the reverse bias, okay? That's why it's also known as a avalanche process, kind of like, on a hillside, if you have a snowball, initially it starts out small, but as it rolls down the hill, that can trigger an avalanche, okay?
So, quick question on that. What was the sort of starting condition for an electron to get enough energy to cause this impact?
Yes, very good question. So look at this part of the P side. On the P side, have a few minority carrier electrons, right? Here, they don't see an electric field, but they're not static. They're always executing random Brownian motion with a kinetic energy half mv squared equals KT. You'll notice that I'll figure out how to make my pen narrower. I thought it could be done, but once one of the students mentioned it, even I can figure out these things. So hopefully you can read the stuff more easily now. Anyway, so half mv square equals thermal energy KT. So that's your random Brownian motion, okay? Accidentally, some of these electrons might diffuse through this random Brownian motion to the edge of the depletion region. And that's where they start seeing this electric field, right? And that's what triggers the gain of kinetic energy of the primary electrons. And once it gains energy in excess of the band gap, it can cause this impact ionization process. Okay?
Okay, thank you.
Now, these breakdown voltages, either through Zener tunneling mechanism or this impact ionization or avalanche breakdown, are plotted over here for what are called one-sided abrupt junctions. Okay, one-sided abrupt. But it's hard to write on this iPad. It's kind of like when I go to the grocery and I sign, you know, I can't recognize my own signature. It's kind of like that. Anyway, so one-sided abrupt junction. What does this mean? In an abrupt junction, basically what I'm saying is the doping concentration is constant and it changes abruptly to the other doping concentration. Practical junctions don't have to change abruptly like that. The term one-sided refers to the fact that suppose I have a PN junction like this, I may have a very high doping, say on the P side, and I show that as P plus or P plus plus. Those are called one-sided abrupt junctions because now the depletion region will hardly spread on the P side. It'll spread out mostly on the lightly doped side of the junction, all right? In many cases, we'll do our analysis in terms of one-sided abrupt junctions because then, you know, the math becomes simple. You just look at what happens on the more lightly doped side of the junction. And then once you get that expression, you can kind of extrapolate to what would happen if the doping was comparable on the both sides. Anyway, these are for one-sided abrupt junctions. So here I'm looking at the doping on the lightly doped side. And essentially what I'm seeing is, as the doping goes up, this is on a logarithmic scale, the breakdown voltage goes down. And as someone pointed out, answered correctly, silicon has a higher breakdown voltage than germanium because germanium has a lower band gap. And that's true not only for tunneling breakdown, but it's also true for avalanche breakdown, which is in this regime. So this part of the breakdown is due to avalanche impact ionization because the doping is not too high. Therefore, the depletion regions are kind of wide, too wide to allow tunneling. But at the same time, it can allow impact ionization processes because that gives electrons and the holes enough time and space to gain enough kinetic energy to cause this avalanche or impact ionization breakdown process. All right. Now here also the breakdown decreases if the band gap is smaller, obviously, because the electrons and the holes wouldn't have to gain quite as much energy to cause impact ionization if the band gap was smaller. So lower band gaps in semiconductors always will cause lower breakdown voltages, both for avalanche breakdown or for Zener tunneling breakdown, which is over here. So basically what happens is, as the doping concentration increases, the depletion region becomes narrower and narrower, and at some point, tunneling breakdown is easier compared to impact ionization breakdown. Now the IV characteristics, once you have breakdown, are shown over here. Now this part, I'm going to zip through because it's not as important as the IV characteristics of PN junction diode analysis that I spent a lot of time on, but very few quick comments. So such devices can have simple circuit applications that you may have seen in E438 or 302. They can be used as voltage regulators, for instance. Okay, so if I take such a diode and I operate it in the breakdown regime and I hook it up to a simple resistor like this, and I supply a voltage, say a sine wave with a mean value of 17 volts, but the diode has a breakdown voltage of 15 volts. So what's going to happen? I'm supplying a voltage to the diode in reverse bias with a mean value of 17 and a sine voltage, right? But that causes such a high current to the diode that all that extra voltage above 15 volts would be basically dropped across this load resistor. And what you'd measure at this output would be this 15 volts that this diode clamps the voltage to, right? So that's a very simple voltage regulator, okay? And these you can buy in the market. These are sometimes known as Zener diodes. The ironic thing is, if you have a voltage regulator which regulates at a voltage in silicon above, look at this chart, above about 6 volts, it's really breaking down by impact ionization, not by Zener mechanism. But people call those Zener diodes in these voltage regulators, okay? You can look at the IV characteristics of the diode. It conducts very easily in the forward bias, hopefully not at all in reverse bias. So that's an ideal diode. A practical diode looks more like this. So you can then model these characteristics, IV characteristics, using what are called equivalent circuits. And for example, in a diode, you can model that using, I don't know if you guys have done circuit simulation using SPICE. So what you have is you have the ideal diode corresponding to this, but it only starts conducting above the so-called cut-in voltage. So you can model that with a voltage source, which reverse biases the ideal diode. And then in forward bias, current really doesn't go up steeply like this. There's always going to be a finite slope, and that's modeled by a forward series resistance and things like that. Now, in an ideal diode, you'd like the diode to not break down easily in reverse bias and not leak so much. So there's tricks that people use to increase the breakdown voltage of a PN junction. I'm not going to go through this in detail. I'm also not going to test you through that, but very quickly, what people do are tricks like you take the PN junction and you purposely grind the edge, because the diodes tend to break down easily at the edges. And by grinding it, by so-called beveling the junction, you basically magnify the physical length of the depletion region compared to the vertical length. And if the length of the region increases, electric field times depletion width is the voltage. So you can kind of geometrically magnify the reverse breakdown voltage, okay? Another trick that's used is, if I make a PN junction, this is a cross-sectional view, you can purposely put in what are called guard rings. These are low-doped doping collars right near the vicinity of the junction. By having a lower doping in the so-called guard ring, you expand the depletion width. And once again, a wider depletion region means a lower voltage. Kind of along the same lines, another trick that's used is to make what are called PIN diodes, okay? The I region is a very lightly doped region. Might be slightly N-type or slightly P-type, but very, very modest doping. Those are called PIN diodes, I standing for intrinsic. And basically under those conditions, the depletion region expands very, very easily across the I region because there's hardly any dopants over there. And basically you then get electric field profile where you have electric field lines from the exposed donors going all the way to the exposed acceptors on the P side. Okay, so there's hardly any charges to terminate the electric fields. So as a result, the electric field in the I region is going to be constant. It's like a charged dipole from here to there. And if the electric field in the I region is constant, that's reflected by a constant slope. So now this band diagram really has a straight line. It's not that parabola connected to an inverted parabola as in a regular PN junction that I mentioned earlier on, okay? I'm going to skip the next slide entirely. So there's a very interesting device called the Esaki diode with a very interesting negative differential resistance characteristics. Those are not that useful, it turns out, so I'm going to skip that in the interest of time. Now, what I want to conclude today is by looking at some of the non-idealities of the diode. Okay, so I've spent the earlier part of the lecture today rehashing the Shockley ideal diode approximation for a long diode under low level injection condition. So those are the three assumptions that we made. So the ideal diode approximation was, we said that there's no generation recombination of carriers within the depletion region. All the generation recombination was in the P or the N side, right? That's the ideal diode approximation. Well, that's not true in practical diodes. And that's the first approximation that we get rid of, okay? So it turns out in a real device, you'll always have some defects such that you will have generation processes or maybe recombination processes in forward bias within the depletion region also. Now this band diagram here is focusing on the generation process, which is applicable in reverse bias. Let's look at the IV in reverse bias. That's forward bias, reverse bias. We said that it's a voltage independent current, right? That's only true in an ideal diode where there's no generation recombination within the depletion region. Okay, in a practical device, if I have defects, that can give rise to energy levels at these recombination sites, which are called ER. So now, in reverse bias, where the bands have been skewed as shown over here, where the N side energy levels have been pulled down, P side has been pulled up, and I have a wide depletion region W, what's going to happen is, because I have defect levels in the middle of the gap or somewhere in the gap, it makes this process of exciting electrons from the valence to the conduction band much easier. Okay, because now you can do it in 2 steps. It can excite from the valence band first to the energy level, and then from the energy level to the conduction band, right? And that 2-step process is going to be easier than a direct excitation from the valence to the conduction band. And that analogy that I'd used before spring break, I don't know if you remember, is citing my arthritic legs. And I said that if you asked me to step onto my desk, I wouldn't be able to do that. But if you gave me a stool, sort of midway between the ground and the table, I could step onto the stool and then from the stool onto the table, right? Now, of course, the stool has to be sort of midway between the ground or the valence band and the tabletop, which is the energy conduction band over here. Because if the energy levels were close to the conduction band, for instance, that would make this process very easy, but the valence to conduction, valence to defect level becomes much, much harder, right? So the most effective generation recombination sites are the ones that are so-called deep levels near the middle of the gap, okay? If they're shallow traps, either close to the conduction or the valence band, they're not as effective. The bottom line is, if I have a lot of defects near the middle of the gap, that reduces the carrier lifetime in the semiconductor tau, okay? And that then adds to this generation recombination leakage current, where it doesn't flatten out as a function of voltage, but increases as reverse bias goes up. And that's what's shown over here. Why does it go up? Well, you get a generation rate of minority carriers, which is given by the minority carrier, the intrinsic carrier constellation Ni divided by 2 times tau, where tau is this generation recombination lifetime. Okay. Now I'm not going to go through the derivation of that, but hopefully that's kind of reasonable, because if I have a low lifetime because of a lot of defects or defects near the middle of the gap, your lifetime will be smaller. Therefore, the rate at which I excite electron hole pairs, which is Ni divided by 2 times tau, would go up, right? That gives you the particle generation rate, electron hole generation rate per unit volume. To get the total current, you then have to multiply by the volume of the depletion region, which is the width of the depletion region W times the cross-sectional area of the diode, A, right? So A times W is the volume of this depletion region, right? The width times the cross-sectional area of the device, A, right? Times Ni times 2 tau gives you the generation rate of electron hole pairs per unit volume. So that volume times that gives you the total number of electron hole pairs. And then to get the actual current, you have to multiply with the charge of the electron. You with me? So lower the lifetime, tau, by having a lot of defects per unit volume and defects closer to the band mid-gap will cause more and more electron hole pairs created per unit volume, Ni times 2 tau. To get the total carriers, then you multiply by the volume, and then to get the current, you multiply by the charge of the electron, okay? Now that current increases with reverse bias, because as the reverse bias goes up, which parameter over here do you think would change? Any guesses? Does the cross-sectional area change of the diode? Of course not. I mean, that's the physical structure, right? Does Q change? No, that's electron charge, right? Does the number 2 change? I hope not. My math friends will be very upset. What changes? It's W, the depletion rate, right? As the reverse bias goes up, the depletion region gets wider and wider. How does it change? Well, before spring break, when we analyze the p-n junction in equilibrium, you should look back at your notes. We proved one expression, and that is the voltage across the depletion region V is given by half Q, say, suppose I'm looking at a P plus N abrupt junction, one-sided abrupt junction, the depletion region W will spread mostly on the N side, in which case it will be given by half Q ND W squared over epsilon. Okay. Now that's the expression that you might want to memorize, because I'll be using that sort of a expression again and again, not only for PN junctions, but later on for MOSFETs and MOS capacitors also. Of course, MOSFETs and MOSFETs are not PN junctions, but there, when you look at the depletion region in a MOSFET, we'll be solving the Poisson equation there also. And the solution of the Poisson equation will have the same form in the depletion region, regardless of whether I'm looking at the depletion region of a diode or a BJT or a MOSFET, MOSCAP. So this result that we got by solving the Poisson equation can be applied not only for PN junctions, but also for other devices. Okay, so I want you to kind of remember this, because we'll be using that again and again, all right? Now the point is, as the reverse bias goes up, the depletion width goes up, the depletion volume goes up, and the reverse leakage current goes up, all right? So that's one non-ideality. Another non-ideality is in forward bias. In forward bias, the bands, of course, would get skewed the other way. The barrier would reduce to V0 minus forward bias. You inject holes from this side, and they now appear as minority carrier holes and the diffuse and all that. Now, in the Shockley ideal diode approximation, we had said that any hole that is injected doesn't recombine, and therefore we said that the current was constant throughout the depletion region. Then it goes down exponentially with distance, right? Similarly, for the electrons, they're injected as majority carriers, but once they go over, they're now minority carrier electrons on the P side, and that goes down exponentially with distance. Initially, we assumed there's no generation recombination within the depletion region, therefore that current was assumed to be constant. Once again, that's an approximation, right? In a real device, if I have defects like this, once I inject holes from this side and I inject electrons on this side, there is a chance that they can recombine partly within the depletion region itself, all right? Now, because of that, I'm now going to go to the mathematical analysis. One finds that the IV characteristic gets modified, and all that happens is you still have an exponential dependence on voltage, but you now add a second factor, the so-called diode ideality factor N, where N can range between 1 to 2, 1 if it's an ideal diode, and 2 if it's a really crappy diode, where every carrier that's injected gets recombined with every carrier that's injected this way, and all the recombination happens within the depletion region. That does not mean that the current vanishes, right? Because it's kind of like, I have to keep supplying carriers this way and this way, but most of the recombination might happen within the depletion region, in which case the ideality factor would be 2. Practical devices are somewhere in between, and a good silicon diode, just for calibration, will have an ideality factor between 1.05 to 1.1 or so, okay? So you can measure that experimentally, and if it's much higher than that in silicon, you have a problem with your device.
So, quick question on the equation that you wrote at the bottom of the last slide.
Okay.
What is the variable in the denominator? Is that an F or an E, or what does that represent?
It's E is the exponent, exponential. E to the power charge of the electron times voltage over diode ideality factor N. That's a new term that I've just introduced, okay? So N is called the diode ideality factor, okay?
Okay.
KT.
I was referring to the voltage, the 1/2 Q in D W squared.
Over here. This one?
Yes.
Oh, okay. So that's a voltage drop across the depletion region. It's equal to half Q doping on the lower dope side of the junction, W squared over the dielectric constant of the semiconductor, epsilon. So that's epsilon.
Okay.
So that's epsilon naught times the relative dielectric constant of the semiconductor. So if you look back at your notes before spring break, we derived this expression over here, okay?
Okay, thank you.
All right. Next approximation that we'll get rid of is this low level assumption, okay? So low level, once again, remember, we said that if you look at the majority carrier concentration divided by the minority carrier concentration is given by e to the power q voltage over kT. And that voltage could be the V naught minus forward bias or V naught plus reverse bias over kT, right? Now, in the low level injection condition that we just, discussed at the beginning of this lecture, we said that the numerator, which is the majority carrier concentration, does not have a significant change on a fractional basis, okay? Delta P is exactly equal to delta N on the P side, okay? But delta P on the P side is much, much smaller than the P doping on the P side to begin with. That's the low level injection assumption, all right? And that's why we're able to say that when I have this ratio decrease by e to the power q V naught minus V, that's why we're able to say that P on the N side was e to the power, it was the starting value Pn naught, e to the power qv over kT, and the excess was -1, right? That was the analysis that we did. Well, it turns out, if you keep cranking up the voltage, forward bias more and more and more, as the minority carrier concentration goes up, so will the majority carrier concentration by exactly the same amount to maintain space charge neutrality. And at some point, you can no longer claim that the change of the majority carrier concentration is negligible compared to the starting value, right? If you keep cranking things up exponentially, right, at some point, the change will also be significant on a fractional basis. And that's what high level injection means, all right? In this case also, I'm not going to go through the detailed mathematical analysis, but basically that introduces a factor of 2 in the exponent of this IV characteristics, kind of like the diode ideality factor. But here, this factor of 2 is not because of defects in the device, but simply because of high level injection conditions, okay? You can kind of roughly see why that is, because in forward bias, you get the Pn product equal to Ni squared times e to the power splitting of the Fermi levels, quasi-Fermi levels over kT. Now, the splitting of the quasi-Fermi levels is given by the applied voltage. Now, in high-level injection conditions, P and N become kind of comparable, as I just said. Therefore, either P or N is now going to be e to the power QV over 2 kT. So that's the origin of this factor of 2 in the exponent over here, okay? Final non-ideality is due to so-called resistive or ohmic effects, okay? And that's shown in this cartoon view over here. So basically what happens is, as I flow current, remember we said that most of the voltage is dropped across the depletion region because that's the most highly resistive part of the structure. But don't forget that the undepleted P and the N region also has a certain resistance, which I call now RP and RN, right? And if I flow a current far away from the junction, remember we said that it's majority carrier drift current, right? It's only diffusion current in the vicinity of the depletion region, but very, very far away where the carrier concentrations have, flattened out to a constant value, there cannot be any diffusion current. Therefore, on the P side, it's got to be mostly majority carrier hole drift current. Similarly, on the N side, far away, it has to be majority carrier electron drift current, right? Drift currents require electric field. Therefore, the integral of the electric field times distance will imply a voltage drop. Now, the electric field is going to be very, very small because you don't need a high electric field to sustain that current because you have such a large number of majority carriers, right? But the electric field will not be 0. So in these band diagrams, when I show these bands as flat, strictly speaking, it's not true. There will be a gentle slope, okay? But I can barely see it on this scale, right? And that low electric field will be able to drive this current, which has to be constant throughout, according to KCL, right? The electric field only needs to be a small number because you have a plentiful supply of majority carriers on the 2 sides, all right? But that IR voltage drop is shown over here, okay? Now, essentially what happens is, in forward bias, as I plot I as a function of voltage, as the current goes up, this IR voltage drop across RP and RN cannot be ignored, and at some point that becomes important and the curve bends over. You don't keep going up exponentially according to the ideal diode expression. So all these non-idealities are summarized in this plot. So on the right-hand side, I look at the forward characteristics. now on a logarithmic scale. Okay, so now let's write down the expressions. I equals some constant reverse saturation current e to the power QV over N KT minus 1. So when voltage is 0, of course, the current has to be 0. E to the power 0 is 1 minus 1. In reverse bias, this term, the first term basically becomes negligible, and I get a minus constant I naught. But in a practical device, we saw that you can have extra generation recombination in the depletion region. And then at high enough voltage, you can get breakdown, hopefully not catastrophic breakdown, due to either Zener or impact ionization mechanisms. Forward bias is more interesting. Well, in forward bias, you can kind of ignore the 1 because, you know, this exponential term dominates. So in that case, then, if you take the natural log, you get natural log of I equals log of I naught times log of the second term. What is log of an exponential? It's just the exponent, right? QV over NKT. So now if I plot log of current divided by I naught, so I bring this over to the left-hand side. I'm bringing it over to the left-hand side. And I plot it as a function of this voltage, VF. I'd expect a straight line, that's N. Get messed up. If I plot it as a function of V, I should get a straight line with a slope of Q over N KT, right? Now what I find is, if it's an ideal diode, which is this regime, I get an ideality factor or slope of 1. But if I get low currents, I get an ideality factor N equal to 2, and that's a factor of 2 that I mentioned over here, right? Because of recombination in the depletion region. On the other hand, if I go to very, very high currents, I also get an ideality factor of 2. But this ideality factor of 2 is because of this high level injection condition over here. And then for even higher currents, the curve doesn't increase as steeply, doesn't increase exponentially, then it bends over because most of the applied voltage now at these high current levels ends up getting wasted across this series resistance Rn and Rp. So that's what a practical device looks like. Okay. Now, one question you might ask is, in a device, suppose I have defects where I start out with generation recombination dominated current with an ideality factor of 1, why would then change over to an N of 1, from N of 2 to N of 1? It's the same device that I'm looking at, right? But here I can use an analogy, okay? The analogy that I use is, last year, I took my family to safari in Africa, Serengeti. And I don't know if you've seen these National Geographic videos where during the migration, these wildebeest go across this river. It's called the Mara River. And there's crocodiles in the river. Okay, so initially what happens is a few of these wildebeest try to cross the river and the crocodiles grab them. Okay, so that's your recombination process of the carriers. Okay, but pretty soon the wildebeest are smart, and instead of going across ones or twos at a time, they just make a mad dash across it. Okay, and what ends up happening is, while the crocodiles are busy gobbling up the first few wildebeest, they're busy, and the rest of them just make their way across. Okay, so you can think of these generation recombination sites as your crocodiles in the river, and the electrons and holes as the wildebeest going across. So if there's a trickle of carriers, the crocodiles or the generation recombination sites can gobble them up. But as the carrier concentration flow across the device goes higher, at higher current levels, the vast majority of them survive the journey because the traps are already occupied, and therefore the ideality factor changes from 2 to 1. Okay? Any questions? I know we're at the end of our time, but I want to quickly mention one slide because that'll tie up the IV characteristics. And next time we'll start with CV characteristics. So the other assumption that we had made was we had looked at a long diode, right? And because it was a long diode, if you look at the carrier concentration profile as a function of x, by solving the continuity equation, we have some C1 e to the power minus x over LP plus C2 e to the power plus x over LP. Remember that? Now, for a long diode, if x is very, very long, the second term would have blown up. And that's why you're able to ignore the second term. And that's what we retain, just the decaying exponential term in the IV analysis, right? But if I make my diode length L smaller and smaller, small compared to the diffusion length, I can no longer ignore the growing exponential term, right? So that's why in a short diode, or a so-called narrow base diode, you have both the decaying exponential and the growing exponential term. And the analysis then, it's the same kind of analysis, but now you have growing and decaying exponentials, and that then results in hyperbolic functions, cosh and sinh, and so on and so forth. And then you have cotangent hyperbolic as shown over here, okay, for the IV. Now, cotangent hyperbolic is the ratio of cosh over sinh. Cosh is e to the power x plus e to the power minus x over 2. I'm not showing the 2. Sinh is e to the power x plus e to the power minus e to the power minus x over 2. The 2's cancel out, okay? Now, the sinh is basically proportional to the x, while cosh is proportional to 1. So I get 1 over x for low values of x. So therefore, cotangent of L over LP, you flip that and you get this, okay? And you basically get, in a short diode, the IV characteristics, which depend on this form, okay? So you still have this exponential dependence on forward bias. But now, what you find is the carrier concentration profile, instead of dying down exponentially with distance, is pulled down to 0, almost like a linear profile, okay? Therefore, you get 1 over L, where L is the length of the diode, rather than 1 over LP e to the power minus x over LP as you had in a long diode, okay? So that's the expression for the IV in a short diode. Now, this will become very important in a few weeks when you look at bipolar junction transistors. So keep that at the back of your mind. So there you have an emitter, a narrow base, which is like a short diode, and your reverse bias collector, and you have a carrier concentration profile will be more or less linear in the base region, where you have a forward bias emitter base junction and a reverse bias collector base junction. All right, any questions? See you next Monday. Be safe.